the boundary layer thickness is much smaller than the dimension of the wall. And second, because most recently the topic was the thermal boundary layer, the assumption was that the thermal boundary layer of thickness delta sub t is actually thinner than the velocity boundary layer called delta. And that means in kind of the stick drawing of a kid from kindergarten, it means that if the velocity profile is this way, with u infinity at the very top, the temperature profile is this way, with T0 here and T infinity in the free stream. So what's bathing the wall is a uniform stream of temperature T infinity and horizontal velocity u infinity. In other words, the analytical expressions that we discovered last time refer to this relative comparison between what's stuck to the wall and not moving as fast as the free stream, and what is heated next to the wall to a temperature sensibly greater than that of the free stream. You see? And by the way, this comparison led to the aha at the very end of my lecture last time, that the velocity scale in the thermal boundary layer region, which by the way is the region of interest when we teach thermal boundary layer, the velocity scale in this region, a scale called u in the layer of thickness delta sub t, that scale is smaller than u infinity, smaller by the ratio delta sub t over delta u infinity. This proportionality comes from comparing two similar triangles, this one, the big one, and then the smaller one. All right, the results that came from the analysis, results that are already in your notebooks, and once again, you are urged to write by hand with from mind to hand to pencil to the paper, to write your own notes of this lecture, meaning don't write down my lecture, write your own lecture to yourselves. One day, if you have a moment or 10, drop by my office and I'll show you my notes from when I was an undergraduate and graduate student, from very famous professors such as Dan Hartog. I talked about him last time. I still use those notes. I also purchased their textbooks, because at MIT professors taught out of their own books. They're not reusing other people's stuff. That would have been sacrilege. So anyway, the result was that delta sub t is of the order of Prandtl to minus 1/3, and then L, and then Reynolds based on L to minus 1/2, where the trailing product is the old acquaintance called the velocity boundary layer thickness. And with this discovery in hand, we know the scale of the heat flux. The heat flux is this stream of, it's like skiers down the slope, stream of energy per unit area called heat flux. Which is of order K, and then the temperature difference delta T, capital delta T, The temperature difference is obviously this one. Divided by the distance, meaning the distance traveled by the heat flux, which is delta sub T. This statement is the so-called law of Fourier from heat conduction. It is not a law, it is an empirical relation trumpeting the obvious, which is that you have heat flow if you have a temperature difference. If you use this idea from Fourier, then you can measure both the heat flow and the temperature difference. Dividing the two, you find the coefficient, the factor called thermoconductivity. So thermoconductivity is, just like viscosity, a proportionality factor that's measured and tabulated forever by measuring both sides of this equation, if you write it exactly. Get it? It's not a law. This is not a statement of universality among phenomena, because there are lots of relationships between heat transfer rate and temperature difference that are not linear. They are not proportional. They are how should I say, what's the word? To one value here corresponds another value here, but they are not proportionalities. Okay? And incidentally, this was not invented by Fourier, it was invented by Biot. I'll get next to what Fourier added. Biot was almost one generation ahead of Fourier, therefore Biot belonged to the, he lived through the French Revolution in the late 1700s. Okay. What do you do with this? Obviously, you substitute everything that I wrote above. So heat flux, and then you say K delta T, and then the upside down of delta, which is Prandtl to 1/3, 1 over L, and then Reynolds to 1/2. And next comes one of the, let's call it the strengths or the vices of heat transfer, for that matter, fluid dynamics. People in these fields have fallen irreversibly in love with expressing their results in dimensionless form. And the dimensionless form is useful because it is, first of all, compact. It is always correct because it is dimensionless. You cannot make mistakes of apples and oranges. But you need to know the meaning of the definitions of these dimensionless expressions. If you screw that up, meaning the definitions in your head, then you are in worse shape than you are with this kind of result. So this is dimensionless. I mean, not this, these two, 1 and 2. The other ones are not. So we're therefore putting everything on the left, namely heat flux, L, and then K delta T. Let me put it this way, delta T and then K. And then the right-hand side is Prandtl to 1/3, and then Reynolds to 1/2. At this stage in the back of the envelope comes the idea that if there is temperature difference, there is heat flux. So the ratio was called by Fourier now H, or heat transfer coefficient. H, heat transfer coefficient. Get it? So the dimensions of heat transfer coefficient you can see from this box would have to be the dimensions of conductivity divided by length. So they are, that's conductivity, and then divided by length means watt per meter squared K. Those are the dimensions of, of heat transfer coefficient, as they should be, because the dimensions of heat flux are watt per square meter, and the dimension of temperature difference is degree Kelvin. And so heat transfer coefficient is not to be confused with thermal conductivity, which has the dimensions of watt per meter K. From this other definition, where was I telling you about BO? I was telling you about BO right here. You see heat flux times length. All right, divided by temperature difference. All right, so we have a dimensionless expression for so for the newborn, this expression, which is valid for this kind of a comparison. Next, speaking of falling in love irreversibly with the dimensionless notation, this group on the left-hand side, 100 years later, acquired the name of Nusselt number. He was a contemporary of Prandtl. So the Nusselt number is shorthand for heat transfer coefficient times the length scale, in our case L, divided by K. It is used in convection. So don't be confused by this thermal conductivity, which smacks of heat conduction. So notation from heat conduction is useful. But if you use it in convection, it doesn't mean that your phenomenon is conduction. It is convection. So keep your Nusselt number in the back called convection and understand. By the way, it would really help you if you read about the lives of these individuals. Nusselt was, this is now early 1900s, a pioneer, a big one in condensation. You'll see later in this course. He did the boundary layer theory of condensation. In other words, what flows as a film down a cold wall exposed to steam is like a boundary layer, and that flow, in this case of a heavy fluid surrounded by lighter fluid, which is the steam, is the difference, but conceptually is the same problem as Prandtl's boundary layer theory. Anyway, Nusselt. I wrote it here. If you don't remember the name, remember walnut. Walnut. Nus means walnut, or in the supermarket it means all the other nuts. I'm talking about the actual, the seed inside the pit, or whatever you call it, the one you eat. I'm not talking about human misbehavior, You've heard that, The word nut has many uses in English, especially in the plural. Here we go. So that was the review of the last lecture. Next comes... Yeah.
So you mentioned K has been there's been tables made of it. Is it typically derived empirically, or can you derive K, and for that matter H, analytically based on material properties?
In physics, again, latecomers, this is 100 years after, meaning the late 1800s, physicists rode that particular horse in the direction of predicting from molecular physics some of these proportionality factors. They were successful, according to the undergraduate courses I took, with regard to ideal gases. That's called the kinetic theory of gases. And I don't teach that. I don't teach that. It's much better to understand the originals and then to build on the originals your own dreams of last night. The original work is and for that matter, the original author. These two are the best sources. They also teach the audacity of exploring the unknown, compared with checking this textbook and then this textbook and all of that. Forget that. That's not for people who come to Duke. All right. So now there's one. Let me question myself here for your benefit. Why did I use this expression from conduction in an analysis of convection? Conduction is for things that don't move. This flow is scraping the wall. Everything is moving that's above the wall. What's your right, Adrian, to play this trick on the audience? Well, it is not a trick, because, as I've said many times, this is a viscous fluid. It sticks to what it touches. So, in extremis, right at the wall, the fluid is stuck. It is not moving. And it is right at the wall that I invoke the Fourier relationship between, Biot relationship between heat flux and temperature difference. Right at the wall, in that extra thin layer of the slender layer. Get it? And it is not a trick. It is the way things are. But I bring up the name of Biot. So what is then Fourier's contribution? It was to introduce this second proportionality factor and to proclaim that it is not to be confused with the older one. So there are two things in heat transfer, in this case in the presence of motion: conductivity at the intimate contact, and heat transfer coefficient, which speaks of the clearly of the ability of the flow to carry energy or heating downstream. All right. So when when is delta sub t smaller than delta? Well, we find the answer if we pendulate in the opposite extreme. I spoke last time about the two extremes and the fact that all of us live between those two extremes, literally. You'll see very soon. Convection in air is exactly in the middle of the so-called distance between this drawing and then the opposite of it, which is to assume that delta sub t is much bigger than delta. That drawing is this one. It's just like this one here, except that you switch these two deltas. So you got a thin one called for velocity and a thicker one for temperature. So the velocity boundary layer is this. The temperature boundary layer is this one. And so U infinity, forget that, U infinity, and then T infinity here, and then T0 here. And important, and that's why I repeat, the system that you contemplate is a fluid layer of thickness delta sub t and length L. So at location L, you have this thermoboundary layer. And in that region, the governing equations are, of course, valid everywhere, including in this region. So the energy equation is, well, anyway, it's steady state U dt dx plus V dt dy equals alpha and then d2t dy2. We've gone through these steps, scale analysis. You end up with, well, for the delta t divided by x, you get that. And u, the scale of u in this thicker region is u infinity, because this original delta is as small as you wish it to be. If you disagree with me, I'll make it even smaller, and I'll draw it even smaller, to the point that it's so small that people call it slug flow, a flow that sweeps the wall with uniform velocity, like the sweep provided by the bullet exiting the gun barrel. That is a flow with uniform velocity profile, but with a temperature gradient between the bullet and the barrel. Why gradient? Because at the interface there's the generation of heat by friction, and that's a problem of its own, worth contemplating. The scale of u is u infinity. And then you have another possibility here, the scale of v at the edge of this boundary layer, delta sub t, delta t over delta sub t. And then on the right-hand side is alpha delta t over delta sub t squared. You'll notice that I'm repeating things I've put on the blackboard before. I repeat them obviously for your benefit, but also for my own dexterity. I like simplification. I also like the point I made earlier that the equality between these two balloons, that equality is proclaimed by mass conservation, which I did not write. And what's left is that the scale u infinity over L is the same as, alpha over delta sub t squared. And what is the physical meaning of simple relation? Like, listen, if it's simple, the relation, the physical meaning should be nakedly evident, like the corpse at the morgue, you know, obvious. What is that? The left-hand side of that came from here, which has to do with flow. Flow on the, let's call it warmth on the back of a flow. So the left-hand side, people call it the convective side of the energy equation, refers to energy being carried from left to right as the stream sweeps the surface. The right-hand side is about temperature gradient, in this case curvature of the temperature field, obviously in the vertical direction, which means heating extracted from the wall by the sweep. It's actually the other way around if you think about it. If the wall is warm and then here comes this cold stream, the wall is doing its thing, and the stream is then sweeping the hotness downstream. And that is the idea that led me, when I was not much older than all of you, added together and divided by 10. The point is, so this thing that I discovered in 1983 is the so-called concept of heat line. Heat line, the actual path of this heating that comes out of the wall and then gets swept downstream. So if this is the boundary layer, and it doesn't matter whether there's the thermal one is thin or thick, it has this shape, as we discussed. And coming out of the wall, imagine uniform heat flux. You see, the drawing of a heat flux distribution is like the drawing of stresses, uniform stresses. The drawing is identical because both the stresses and the heat flux are invisible. They are in a graphic representation of your imagination. Anyway, so the heat flux comes out uniformly through the surface. And instead of going upward, as it should, because above the surface the fluid is cold, that line, initially vertical, gets bent to the right. So the actual path of the injected heat input is this. And those are the heat lines which is a concept or a graphic technique of opening people's minds to the reality of convective flow. It is taught in the textbook in sections 1.6 and 2.11. So that's the physical meaning of first of all, convective heat transfer. But what we do with this expression, okay, so we got this proportionality. It means, well, we just turn the crank, delta sub T squared, the same as alpha L divided by U infinity. And then, because we are enamored of dimensionless notation, we among other things, we're enamored of dimensionless notation, divide by L squared, and conclude that delta sub T over L is the same as this number alpha over U infinity L alpha U infinity here, L to power 1/2. And you see on the right-hand side a group, the upside down of which is familiar. U infinity L over nu is the definition of the Reynolds number based on L. Nu is the kinematic viscosity, also known as momentum diffusivity. Down here, instead of nu, you have alpha, which is the thermal diffusivity. So now you get the idea that the field grew, not because ideas multiplied, but because the notation repeated itself with slightly different symbols. So this other group, U infinity L over alpha, is known as the Peclet number. Peclet number. At the time of, shortly after Napoleon, there was a famous professor at the, I believe this is 1830s, at the National Conservatory of Arts and Professions in Paris. Anybody's been to Paris? I highly recommend. Immediately north of the Pompidou Center is the oldest, it's like they teach here this engineering management program. In other words, more applied version of the École Polytechnique. École Polytechnique is the oldest engineering university in the world, but it still is a military university because that's the origin of engineering, as I've told you more than once. But north of it is this university goes by the initials of CNAM, Conservatory of National Arts and métier means professions. Anyway, so Professor Peclet was the first to write the heat transfer textbook. So for decades after him, meaning generations after him, they learned heat transfer from his book. Peclet number. Clearly, if you multiply Peclet by nu over nu, you get U infinity L over nu, and then, so U infinity, okay, and then times nu over alpha. In other words, I multiply by 1, nu over nu is 1. I did nothing to this expression. So I discovered that the Peclet number is equal to the Reynolds number times the Prandtl number equals Peclet based on the same length scale L. I go through these steps so that you have them down once and for all and not be scared of them. Delta T, under this new assumption of thick thermal, thin velocity, delta sub T is of the order of L, and then this stuff to power minus 1. And that stuff is the Peclet number, upside down, Peclet meaning Prandtl times Reynolds. So here we put, let me do it this other way, Prandtl to minus 1/2, then L, Reynolds to minus 1/2. And this was the old delta. If I divide by delta, it turns out to be Prandtl to minus 1/2. And recognize the inequality, which is much greater than 1. I discovered that this situation, the most recent, is valid for liquids with very small Prandtl number. The inequality, meaning the thick thermal boundary layer assumption, is valid when the Prandtl number is much bigger than 1. Oh, sorry, much smaller than 1, if that's the case. And the fluids that are famous for low Prandtl numbers are those famous for huge thermal conductivity. Those are the liquid metals. So liquid metals, such as liquid mercury. When I was an undergraduate and graduate student, nuclear reactor engineering was a noble form of engineering. Then it went into disrepute. There are very few departments of nuclear engineering in America. I think the interest in that science and technology is coming back to life, and there's a future to it for all these concerns about the sustainability of not the planet, the sustainability of humanity. Okay, liquid metals. And that means that on a rebound, the original assumption, which was the thin thermal boundary layer is, so delta T smaller than delta is valid when the Prandtl number is greater than 1. And here we have the distribution of Prandtl numbers of fluids in nature. The Prandtl number, let's call it the scale, logarithmically. So it's 1 here, and then 10, and 100, and so on. And in this other direction, 0.1 and 0.01. We know the conclusion, which is this. By the way, let me translate this in Nusselt number form. Whereas in this limit, the Nusselt number was, as you just reminded me, Prandtl to 1/3, Reynolds to 1/2. If you use this latest expression, you find that in the low Prandtl number limit, Nusselt is of order Prandtl to 1/2, and then Reynolds to 1/2. Which are these fluids that line up on this, ladder from left to right? First, Prandtl number almost equal to 1, more exactly 0.7, which is very close to 1, are the so-called permanent gases. They are called permanent gases because until the early 1900s, you've heard of this company, Air Liquide, a French company. You've heard of it? That was the baby of the French version of Thomas Edison. His name was, still is, Georges Claude. He liquefied industrially air, liquid air, and separated that into all these fractions: oxygen, nitrogen, argon, all the way to helium, neon, all the way to helium. Hint, hint, hint. What else did Georges Claude invent? The neon light, the incandescent tube. If you look at these black and white newsreels from the late 20s, the roaring 20s, the lights of Manhattan, the black on white, sort of white on black, neon lights everywhere, these tubes bent in the shapes of letters and the flowers and all of that. He did it. Yeah. There's a reason you don't hear about him. And that is because during the 2-year-long, I think it was 2 years, maybe I underestimate, of Nazi occupation of northern France, he continued to do business with the Nazis, because he was a businessman, as did many French industrialists. But unlike the other industrialists, after the Americans liberated France, Georges Claude said, "Not my fault, I'm a businessman," whereas the other people apologized. So his story is unique for that reason as well. Anyway, that's permanent was the name for these gases before industrial liquefaction of highly compressible gases became possible. To the right, in this limit, with Prandtl numbers much greater than 100, are the oils. So oils. What about water? Water has a Prandtl number of approximately 6. And because of the drawing I'll make next, water goes hand in hand with the permanent gases because of this the exponent Prandtl to power 1/3. 6 to power 1/3 is essentially 1. Okay? And over here, this Prandtl of 1/100 is that of liquid mercury, and all the other ones that your colleagues are to the left of it, okay? Now, the drawing that goes hand in hand with this, to show you that these two formulas for the Nusselt number, for Prandtl less than 1 versus the other one here, Prandtl greater than 1, they're not much different. So if I plot on the vertical the Nusselt number by the factor that appears in both limits, I get, of course, rising here at 1, a ratio of 1. And then in the low Prandtl number range, there's an asymptote of slope 1. And then in the other direction, the asymptote has a smaller slope of 1/3. So the Prandtl number dependence is essentially not very sensitive to the Prandtl number. It's weak, and for your calculations in this inhabited space, you might as well use this expression for everything that matters, unless you're designing nuclear reactors.